Hi, everyone. Welcome to STEM From's podcast, Where Does Your Journey Stem From? Hosted by myself, Dr. Karina Minardi. Today, we are joined by an exceptional scientist and guest, Katelyn, who is currently a graduate student at the University of Chicago. Let's welcome to the stage, Katelyn. Hey, Katelyn.
Hey, Dr. Karina.
Katelyn is a second-year PhD candidate at the University of Chicago, and a National Science Foundation Graduate Research Fellow, as well as a Neubauer Family Fellow. Using ultrafast laser spectroscopy, she researches how biological systems harness fundamental quantum mechanics to control light-driven processes. Before joining UChicago, she worked in industry as a laser field service engineer. So she actually had a life before graduate school. She is passionate and active in the STEM education, inclusive pedagogies, and advocacy in teaching and research. So we're so excited to have her today on the podcast. So Katelyn, as I usually start off, can you tell us a little bit about you, what drives you as a person, as well as your background?
Yeah, absolutely. Well, thanks so much for having me here. Love the mission of STEM From and really excited to kind of share how I had a life before grad school and then started grad school. So in terms of background, as a lot of people who are into science, I definitely was very curious from a young age. I got a microscope as a Christmas present one year, was always reading, that type of thing. But in terms of how I actually got interested in science as a career path and as something that I wanted to pursue higher education for, it was when I was working an executive assistant job for a postdoc. So she was blind and she was postdocing as a computational chemist. And I was with her during her last year as a postdoc. And before then, I didn't know that a PhD was really meant anything except you studied for a long time. So I was introduced to that in the first instance. And then I learned that you could actually get paid to do a PhD, which was complete news to me. I'm from a relatively small town in Wisconsin where not a lot of people go on for advanced degrees other than medicine or veterinary or those types of things. So that was sort of my intro to this pathway and science as a career necessarily. So through that job is kind of where I got my interest started. After that, I applied to a summer research opportunity at UC Berkeley. And through some connections, somebody knew an ultrafast laser spectroscopist, Dr. Graham Fleming, who I joined his lab then in the summer for my first research experience ever. Looking back on that, I knew nothing at the time. And so it was extremely intimidating for sure to jump into a research environment. There were a lot of cultural things and a lot of rules that you don't necessarily know going in. And so having graduate student mentors in that lab certainly made the jump into this kind of environment possible and helped with a little roadmap of how to actually do this. After that, I went back to the University of Minnesota where I did my undergrad and was doing my undergrad the whole time and started doing some research in a lab there, also in ultrafast lasers. There's a theme. And then COVID hit. And so with COVID, I wanted to make a big change. I had lived in the Midwest my entire life, and I started applying to every single job that had laser in the title across the country. I don't know how many initial applications I put out for post-graduation, but I heard back from one company who requested a phone interview. That I thought didn't go well, but I heard back from them and they were like, hey, let's do a Zoom call. And it was totally online. And I was there in Minnesota and they were there in Scotland. And we were opening an office in Boston. So after that, got the job, put everything in a suitcase, went to Boston, was managing grad school things in the background. And so journey started from an unsuspecting place of being an executive assistant and led sort of cross country to California, Boston, and then back to the Midwest for my PhD.
But I'm dying to know who gave you the microscope for Christmas.
My dad and my mom. There is this tiny little shop in Milwaukee, Wisconsin called American Science and Surplus. And they have so many weird things. They have like blown up dead frogs and like random electronic parts that you can get in like grab bins. Really cool place if you're ever in the Midwest, but they bought it from there because that was one of my favorite stores. And I remember looking at like broken cereal and like sneeze on a glass and look at it under the microscope.
Ew. But yes, I remember those days. Okay, well, thank you for, I think, sharing that and American Science and Surplus. I'm going to have to, if I'm ever back in Wisconsin, I'm going to have to check it out. I am intrigued by your executive assistantship. So how did you actually get that gig?
It was an email that was sent out to the entire chemistry department at the University of Minnesota, which was horrendously formatted since they took it from a Word doc to a PDF. And so all of the text was sort of running on half the page. And it just said, executive access assistant wanted for Dr. Mona Minkara, $15 an hour in big red font. And I was like, oh yeah, $15 an hour. I've never made that much money in my life. I used to work as a heavy equipment operator. I have cleaned a lot of bathrooms. I worked as a horse stall cleaner. I used to work at a garden center, always making like less than $10 an hour. So I was like, 15, wow. And I just sent my email randomly to the email and then had no idea what was actually in store. But in my interview with Dr. Mona, I had mentioned, hey, I think the formatting of your flyer was not great. If I were to get this job, maybe that would be something I could fix, as kind of personal branding, how things look, because she relied on her access assistants to do the visual side of things, though we'd bounce ideas back and forth. The one who's actually trusted to do it is the person who is sighted and at the computer. And so making sure that that work is of high quality as she would like it to be if she did it herself. And so that's how that job came to be.
No, that's, I mean, I've never heard an executive assistant to a postdoc, but given I think her disability, I think that's wonderful. And it's wonderful that the university would also support her in that.
Oh yeah, it was amazing. This entire experience changed my life, and we are still friends. She's a professor now at Northeastern University in bioengineering, which is super cool. But I worked with several others who were in charge of proofreading scientific things, in charge of fine tweaking some code inputs, since she's a computational chemist. And so the Access team was supported by the University of Minnesota, entirely driven by Mona and what she'd like. But in my neck of the woods, I was managing office scheduling, emails, some types of, branding, but basically all of the tasks that we don't really think about that we use our vision for. And those are all the things that, while not directly science, are necessary to make somebody a successful scientist. And that's sort of where my idea of disability advocacy in the sciences started. And so my brother was born with one hand. My dad is physically disabled from an injury. I had always grown up seeing how people with physical disabilities navigate the world, but I'd never thought about it to that extent. And so this was the first time where I kind of thought, wow, there's a lot that able-bodied people take for granted in terms of steering your career, influencing people, managing your life. And that has always carried with me ever since.
Well, that's a very powerful message for sure. You also mentioned connections, and you talked a little bit about, I think, emails and people you've met and networking. And what I've noticed a little bit is that younger students aren't necessarily comfortable with the idea of networking and or how do you actually connect with people at a professional level. And so I was wondering if you could talk a little bit more, not only anecdotally about your connections and how they influenced you, but also about, how did you actually go about doing that?
It is something that is really tough to start doing. I think that in a lot of ways, when we grow up, especially if you grew up in the United States in the standardized school system, it's very individualized. You sit down, you take the test, you submit your own work, and asking for help can kind of be seen as cringe. It's, oh, you should know this, you should be able to study on your own, you should be able to do this. But in terms of actually making those connections, through my experience, it was always through a job or an application. And so I applied to work for Mona, and I applied for the internship program to go to Berkeley. and work for Dr. Fleming. And then I applied to the laser company that I worked for. Those are ways in the door, but it doesn't really stop after that. Because you'll think, okay, I'm here, I'm okay. But a lot of people get internships, a lot of people get jobs, most people have one. And what matters is a bit of humility once you're there. And so utilizing the resources around you, going into every single conversation or interaction with somebody thinking that there's something this person can teach me, there's something that I can learn from them. Whether it's scientific, whether it's interpersonal, whether it's just like a recipe they love, there's always something that you can learn from another person. And through those connections that are very genuine and very humble, you will find a sort of opening up of the world, because everyone has their own little sphere. And the more little spheres that you can get in contact, the larger and larger your own becomes.
I value that, and I thank you for that. I think that is so true, and that's part of not only my mission, but STEM from mission too, is to kind of think at a larger scale around STEM education, and that it's not just about a test and proficiency. It is so much more, so much more. I think there's connections on. I mean, I will speak for myself too, is that I was up for a job and I didn't get it, but the COO called me and said, hey, I want to stay connected with you. And I said, absolutely. And now we're LinkedIn connections and he's going to keep me in mind for a future position. And so it's like, okay, well, maybe one door closed, but he's a great person to know.
Totally. And some of the people that I worked with at Berkeley, we're now looking for a postdoc in the lab that I'm in. And those are the first people that will come to mind for me to recommend to my PI. It's one of these reciprocal things that even though you might be in a position where, oh gosh, I just got here, I don't know what I'm doing, I have nothing to offer, it'll come back around. And that's the thing, is that people inherently, I believe, are good and are generous and understand where you're coming from, as long as you sort of let them. And that can be a big way to foster your career, other people's careers, and maintain sort of the reciprocity.
No, absolutely. I really like that you did a tour de force of industry before you entered grad school, right? And so I'm curious from a point of, what did that teach you? What did that introduce to you?
This might be a bit of a controversial take, but after being in my PhD program for a year and some months, I wish everybody would take a gap year between undergrad and their PhD, regardless of if it's working in industry, working a job that you like at a garden center or something, or just traveling, doing something. Ultimately, what I gained from the industry role was perspective. Through my job, I was a field service engineer. And so I would take on cases of people who needed their laser fixed. Sometimes I would work with them online, but a lot of times I would go travel to their lab, interface with grad students, researchers, postdocs, the PI themselves. And through that, it was an opportunity to develop connections, not only professionally, but to understand how these sorts of things work, how different labs work, how different people interact with each other. And that gave me a really great perspective on the type of lab environment I wanted to be in. I think a lot of people go into grad school and think, oh, I really like research. I just really want to do research. It's okay. There's a lot of cool research going on, but you are a person outside of what you do. And it really matters the type of environment that you are in for the next 4 to 6 to 7 years of your life. If you have some perspective on the type of working environment you'd like to have, what you need to be successful, and how you can support others through your role in a lab, you can find a much better fit going in as a PhD student. And I think ultimately that emphasis on a more holistic PhD experience is not that common. A lot of PhD students genuinely feel like a cog in the machine to produce research, but ultimately you are choosing to do this degree program to have something for yourself. You're not just there to work for someone else. And so that perspective of, hey, this is an amazing, incredible opportunity. I would like to take the fullest by ensuring that my environment fits my needs was probably the biggest thing taking away going forward. Also, I worked on a bunch of lasers, so that's helpful now. But besides that.
Love that. No, I think, gosh, I just thank you so much for that perspective, because I think a lot more graduate students need to actually consider that before they actually choose. You are making a decision, and it's almost like a marriage, for lack of a better kind of comparator. I mean, it really is, because you're going to have people that you work with every single day for 12, 14 hours a day. And you also need to know what kind of mentoring style you enjoy and you can learn from. Some people love micro, some people love macro. And some people love, I don't want to interact with my PI once a month.
A lot of people want to discover that when they first get to grad school. But I think sort of taking yourself out of the academic atmosphere is good. And it's good for development of yourself as a person and sort of interacting with people who aren't the cookie cutter academic style. The way that academia has been built is extremely exclusionary in the first place, not only for people with disabilities, but for people who don't have the same exact cultural background, underrepresented minorities, list goes on. And so understanding how you interact with yourself and with the world where you come from before you go into something that sort of standardizes people in STEM, oftentimes that's what PhD programs will accomplish, can help you maintain a sense of self and a sense to sort of see through when you can actually make things better in the academic system. And so instead of just accepting that, you know what, we don't have that many things in place for disability accommodations, oh well, or coming into it with this perspective of, I've seen this in this university, or I've seen this in this workplace, there's no reason that we can't implement this sort of policy here. And it just sort of gives you ownership, and it gives you an ability to have a new perspective.
So you've lived and breathed industry. You're now living and breathing academia. You're in your second year. What do you think long-term is your career aspirations or goals?
It is constantly shifting, to be completely honest. I was in industry and I was like, this is great. I have a salary. I can go home at 6 p.m. And now I'm in academia and I loved teaching. I love having mentors and mentoring within the lab. I also moderately enjoy the little bit of academic politics that comes with, well, this lab is doing this and I need to do this. And there is a little bit of a competitive edge that's, if you have the personality type, a little bit attractive. And so I originally thought I would go back to industry. I really want to maintain teaching and mentorship and development of people as a part of what I do in the future. And that might be better suited to staying in academia for larger impact. So it is shifting more towards the academic side. I'm not entirely sure that I would want to go to a big research university, maybe something like a smaller liberal arts college where you have a team of undergrad researchers that you can spend a lot of time with and still have very impactful teaching in your courses as well.
No, that's really powerful. Let's shift gears because I want to talk a little bit about your research. Ultrafast lasers. I think that just like came out of the blue and you just decided to go and get your PhD from it. Just kidding. You totally did not, obviously. But you gave a couple of examples of working with your hands in previous jobs. And I'm curious if that's sort of like what lent itself to sort of the aspect of working with lasers.
That is a really, really good observation. And I don't know if I fully put that together yet, but that's totally true. I have always been a hands-on person. I'm a little bit too brash. I don't always think about what I do. I want to solve things. And I really enjoy at the end of the day if I have solved a problem or figured something out. And so through growing up, I always worked on cars and mopeds and fixed things in general. And then in research, if you work with ultrafast lasers, you know that they break almost every day. It's an extremely sensitive instrument, which is highly non-standardized and relying on a femtosecond time scale, so 10 to the negative 15 seconds. Anytime it hits any mirror and continues down the table, something can go wrong. And so I found it very satisfying to think through this multi-step process of, okay, is this okay? Yes. Next thing, is this okay? And actually fixing it. So that's the appeal of lasers. Some people can't stand it. Some people are, I really like process. I want to put in this reagent and then this reagent, and I know how it'll work. Some people, we affectionately call them laser jocks in the field, who just love opening it up, seeing all the bright lights and fixing it, even though the next time, you know, it might break next week. So that sort of constant problem solving and accomplishment was a very natural draw to this specific niche of science.
No, I saw some definite similarities between, I think, yourself and myself, looking at mass specs and big instruments, and I could just take them apart and put them back together, and I loved it. And it was so funny because one time we had a service engineer actually in our lab, and they were like, "Oh, I don't know how to solder this really, really tiny chip on this really tiny other chip," and my postdoc went, "She can." And I was like, "Okay, I'm the solder queen. Hey." And that's one of the only memories that I have from that lab, which is wonderful. But
yeah, you're the best.
Okay, so tell us about your current research. Okay, so you talked about lasers, you talked about the instruments. That's great, but what are you actually doing with them?
Totally. And that's the part that is always, I feel like a scientist who really loves the day-to-day operations has a really hard time with the big picture of, okay, you're getting funded to do what exactly? And so in my PhD, I decided to switch gears a little bit. I still use the instruments, but I have decided to take on a project where I learn protein expression and isolation in order to look at a type of retinal protein. And so the larger class is called rhodopsins. They're really similar to the type of protein that's in the rods of your eye, where it binds a molecule in the center. When light hits it, the molecule isomerizes, and then that forces the protein function. This happens on a femtosecond timescale, which is really great for our systems to understand. And that's where a lot of larger scale, more squishy biological studies can't really reach that ultra-fast timescale. And so biology is incredible in a lot of ways. And in this specific way, it's harnessing some very, very tiny tuned parameters through how the protein has evolved in order to make this process as efficient as possible in some conditions and sort of quench it in other conditions. And with our spectroscopy, we can change the pH that this protein is sitting in to either make it more or less efficient. And then we can watch what actually happens in the molecule. So it gives us a window of understanding of millions of years of incredible evolution in order to optimize this process for visual function, motor function, and some other creatures who use a similar type of protein, and just a deeper understanding of biological photochemistry.
So what is your current hypotheses then?
My current hypothesis, with zero data so far, because I have to learn several years of protein expression in a couple months. That's all right. I've got people to help. My current hypothesis so far is that usually we just think about light process with a ground state and an excited state. In these types of protein systems, depending on how they've evolved, you can selectively access a higher lying excited state to make it more or less efficient. And so through moving your nuclear positions, the state becomes accessible, which is a unique feature because this molecule won't do it unless it's within this protein specifically. So some very deep quantum mechanics, specifically multiple avoided crossings and conical intersections, and strongly non-adiabatic dynamics that have been selectively picked, tuned, and set into motion to create biological function.
When you change the pH of a protein, don't you destabilize it? And are you go ahead, answer my question.
Totally. This is a protein that actually is in the membrane, so it passes protons across the membrane as its function. If you change the pH, it has to function under a wide variety of conditions, so it can still let them cross through the cell. The thing that you're doing in the molecule is you're changing the protonation state of the amino acids in the binding pocket. Through that, we're thinking about our potential energy surfaces. We're shifting all of those around the second you change your electrostatic environment. And so through that sort of squishiness of the potential energy surface, you can tune how your states interact with each other, and you can tune the timescales that these things happen. And so at high pH, we're seeing this happen in my type of rhodopsin at 200 femtoseconds to complete the photo process. And at low pH, it's 800. And so there's a significant difference, even just going from pH 6 to pH 9 in this protein.
Okay, so you're not actually changing the structure of the protein, but you're actually changing the protonation state of the binding pocket. Got it.
Totally. We're just passing around a hydrogen bond and changing that sort of potential energy surface structure around the whole core.
That's awesome. What do you hope to gain from, from understanding, you obviously will understand the evolution of the process, but I mean, would you use this in medicine, in clinical trials, and clinical research, application-wise?
This is, as a lot of 2D electronic spectroscopy experiments, a little far removed from human or biological applications, which is a big qualm that I have with it, as cool as it is. The other interesting thing about this specific protein is that it is in use in optogenetic experiments. So I picked it because of that and because of its cool photochemistry. It also, because it's in use in optogenetic medicinal applications, there's actually an there's an optical hearing aid in clinical trials using gene therapy with this specific protein. So it's useful. You hit it with light, it'll function. You can change that into signals that our brains can process. Your ear and your eye, where it's also being used, and your muscles all have different pH conditions. They all have different charges that move across the cell membrane. They all have very different environments. And so in a little bit of a distanced way, we can understand how this protein will function in different environments and why maybe it doesn't work as well in muscles as it does in the ocular nerve, which has also been seen for this type of protein. And so the initial photochemistry tied to the larger channel function is a study that has yet to be done because these are just such different timescales. But maybe this can inform how we move forward once we've actually hit it with light and let it do what it needs to do.
That's just so fascinating because there's the biology, there's the photochemistry, there's the instrumentation. I mean, you are really working at the apex sort of on all of those different realms, which is just so cool.
We'll see how long it takes to get some data for it. I'm also
after you said you have to actually grow the protein. I mean, that's a whole nother thing.
Yeah, it's a whole can of worms. There's also going to be, because it's really complicated and strange photochemistry, we'll be working with some people to do computational chemistry and some simulations on it. So I'm trying to hit as many subfields as possible to make this project work.
No, that's the essential synthesis of a science paper, is that you have the theory, you have the instrumentation, and then you have the application base. So, I mean, come on, #science.
Here's hoping we'll see in 4 years.
Well, that's a whole nother story. Wasn't the Nobel laureate in physics this year on laser?
Chirped pulse amplification was one of them. I don't know if that was this year. I'd have to look it up. But we use one of the Nobel laureate laser things in order to create our pulse that's short enough to watch these fast dynamics. It was so cool. It was pretty much immediately applied.
Oh, that's so cool. Okay. I was thinking, because I think they weren't femtoseconds. They were aptoseconds.
Attoseconds, yes.
Attoseconds, yes.
Yes, you can only do that with pretty blue light, which will destroy any of our samples. And it's hard to measure a femtosecond, but it's also really hard to measure an attosecond. So it's very niche, extremely cool. You can look at a lot of really interesting stuff. In terms of molecules, we'll see when it gets there.
Yeah. I mean, I think that's the case with all scientific research, right? We'll see.
We'll see.
And hope, right? Hope may not be a strategy, but you still can cross your fingers and hope. So I think my last question to you then, given the landscape, given what you've said, if you were to impart words of wisdom to yourself 10 years ago, or to someone who's even considering kind of STEM, what would you say?
I would say that just because you don't speak the language yet doesn't mean you never will. And also that you don't need to speak exactly that same scientific language. Going into my classes and going into undergrad research and grad research, a lot of people have this sort of old school academic style of knowing professors by last names, people who wrote textbooks, papers by a specific year. I did not grow up with an academic family and know how to do that off the bat. I had seen it and it scared me. It made me feel like, oof, maybe this isn't for me. Maybe I'm not the type of person that should be doing this. But if you have an interest and if you are willing to put in the time, because you'll dedicate yourself to something ultimately. If you decide that you want to dedicate yourself to science, there is space. And there's not only space for you to fit into what exists, there's space for you to influence what's going to exist in the future. So I would also tell myself to just do my OChem homework. It's not that bad. I would say you can take your AP Physics exam. It really is not that bad. You just have to do the readings. Please read the textbook. I know you just want to show up and do the test, but that's not how that works. But yes, that's the sort of overall picture of you can do it and there is work necessary. And also go to office hours, use help, ask somebody you think knows what's going on. They will probably want to help you. And if they don't, they might know somebody who will.
I love all of that. And I value all of that. I would like to add, however, to what you said is that science is a language, and it's a language that you learn, and that some people master, some people don't necessarily master. It doesn't really matter. But the thing is that once you know it, it's so fun to pull it out when you're not necessarily using it, especially with a whole bunch of folks that don't have STEM background. And then you go, oh, yeah, let me talk to you about the,
it's
cycle. Let me talk to you about, spectroscopy. Or, oh, when I was in grad school and I had to do blah, 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 blah. I mean, it's great, honestly.
It's cool. When I go home for Christmas or something, my aunts will always be like, how are the photons? That's what you do, right? Photons. And I'm like, yep, I do photons. It's great.
Oh, yes. I did microfluidics. So I did, how are the droplets? How are the droplets? I'm like, yes, that's all I do is droplets.
It's like you think about it and yeah, I do photons. You did do droplets. The end of the day.
I did. Yeah, if that's someone's takeaway of what our work respectively is, you know what? That's fine. That's how they define it. Totally. Katelyn, with that, this was such a great conversation. I really appreciate your perspective, your point of view, sharing that, and then also sharing your journey. I think you have a wonderful story, and I'm really excited to kind of see the future.
Yeah, well, thank you so much for having me. Thanks for reaching out about this. Yeah, this work is extremely important, and I hope that if somebody feels that they want to continue in science, they should. And there's no shame in not doing a PhD. That's the other side of it, is that you can also be in industry. You can be in industry and not like it. There are many different ways that make this possible. And as long as you have the drive, you have the will, and you have people around you who support you, it's more than possible.
It takes a village for sure. Well, thank you, Katelyn, again. It was such a pleasure. And to our audience, never forget to ask yourself, where does your journey stem from? Bye, everyone.